Hello my dear students, welcome to Deeksha Karnataka YouTube channel and welcome to Masterstroke series where we are trying to discuss both PUC as well as your KCET preparation. So if you are someone who is struggling with your KCET and PUC preparation, then you must watch this series. Here we are discussing the theory in detail, and those who are saying that sir I want the question practice will happen in live session. So please be patient. Whenever you see Masterstroke live, it will start from Saturday. So if you are watching at a later date, maybe live has already started, and don't forget to join in our live session where we will be solving questions, right? So today I am going to discuss a very important chapter, electric potential and capacitance. This is a high weighted chapter in your PU board as well as in your KCET exam. In PU board you are going to get 11 marks from this, and in your KCET exam you are going to get 3 to 4 questions from this chapter. So what we are going to discuss today, so list of the topics: electric potential and potential energy, equipotential surface and electric field, electrostatics of conductors, capacitors and energy stored in capacitors. So these are the concepts that we will study today. Also in between we also have dielectrics, that is I think we forgot it to add. So dielectrics, polar non-polar dielectrics will also be discussed in this lecture, right? Let's start. So electric potential energy. So when we have one charge, okay, and we have one more charge located somewhere, so there will be an electric field force between them, right? According to Coulomb's law, there will be a force acting on this charge. Now if you want to move this charge in the presence of the bigger charge, okay, so you have to do some work, okay. So basically it is same as like a gravitational potential energy, right? The two masses are attracting each other. If you want to move one mass, then you have to do some work on it. Gravitational force is much weaker compared to electrostatic force. So electrostatic force, the work done is more prominent, the force is more prominent compared to gravitational force. But anyway, so if you want to move an object from one point to another, a charged object, okay, in the presence of another charge, then you have to do some work. That work will be stored as energy. And what is the form of stored energy? The energy stored is basically in the form of potential energy. Kinetic energy is energy in motion and potential energy is the energy stored, right? So work done to move this test charge small q is given by WAB. Now you have grown up, so we will not discuss the old form of work done. This is the modern latest form of work done when we are trying to move the charge by a small amount, and we will add all the work done together by integration. Okay, so this is the formula for calculating work done. Okay, why we are using integration? Because normal formula f into x or fx cos theta is 90 degree over sorry, not 90, theta is 0 degree over here, so cos theta is 1. But when we use fx or when we use integration f dx, so that you have to understand, if the force is constant throughout the motion, then fx is sufficient. But here, as you know that electrostatic force depends on distance, okay, and it is inversely proportional to square of the distance. So if you increase the distance, the force will also decrease, right? So based on the distance, the force that you have to apply will also change. So that's why the work done is basically dependent on distance. That's why we have to take the route of integration. Integration route is the best route. Next, this work done against electrostatic force gets stored and as potential energy. So this is the work done against electrostatic force, and it is stored as in the form of potential energy. The work done by external force increases its potential energy by an amount equal to the potential energy difference between the points A and B. So if you do some external work, is it go to waste? No, that work is not go to waste. That work is basically stored as potential energy. So if you study something today, is it going to be waste? No, that is basically stored as your knowledge. So knowledge is same as potential energy. So more you learn, more you gain your potential energy. Okay, so external work that you are putting, the effort that you are putting, will it be going to waste in future? That will not go to waste. That is basically increasing your knowledge. Similarly, the work that is done in the presence of an electric charge, the work will be stored in the form of potential energy. And when you are saying that, so suppose this is your PUC 1, this is your PUC 2. So you have moved from first PUC to second PUC, right? So basically the potential energy difference is the exact potential difference between UB and UA, and that is the work that you have to do. Okay, so the work done is difference in potential energy. Now, at every point in electric field, a particle with charge Q possesses a certain electrostatic potential energy. Okay, the work done by an electrostatic field in moving a charge from one point to another depends only on the initial and the final points and is independent of the path taken to go from one point to other. This is the fundamental characteristics of a conservative force. So electrostatic force is a conservative force. The actual value of potential energy is not physically significant. So as I mentioned, UA and UB, so if you see UA and UB, they are not very significant. Okay, but the difference between UA and UB, that is UA minus UB, this is significant. So exact value we are not super interested, but the difference in potential energy we are very much interested. Okay, so the difference of potential energy is significant. The electric potential due to a system of charges is algebraic sum of all the potential at that point. Okay, so if you have multiple charges and you want to find the potential energy at a single point, you have to calculate the potential energy due to all the charges at that particular point to calculate the potential energy. Okay, potential energy is a scalar quantity. Obviously, potential energy we have learned in our PU1 as well. Potential energy is a scalar quantity. Now let's solve one question from this concept. A particle of mass small m and charge small q is placed at rest in uniform electric field E and then released. The kinetic energy attained by the particle after moving a distance small y is. Very interesting question. So particle of mass small m and charge small q is placed at rest. Okay, electric field is E and then released. The kinetic energy attained. So you have to calculate the kinetic energies. For that we have to use few things. First of all, when there is an electric field, if you place a charge in here, okay, so what is the force acting on it? The force acting on it is given by Q into E. Okay, if the electric field is E, the force is Q into E. We have learned it in our previous chapter, right? So force is charge into electric field. Now what? Now when you are trying to move the charge, say by a distance of y, okay, so uniform electric field means E is constant. Okay, E is constant, so force is constant, so we do not need to worry about force. Now if you want to move the object by a distance y, what is the work that you are doing? The work that you are doing is force into the displacement. Force into the displacement is the work done, right? Now from work energy principle, this is same as change in kinetic energy. Okay, from work energy principle, again first PUC, that work done is basically change in kinetic energy. So kinetic energy change is force into displacement. Now force is given by Q into E, so it will be QE into Y. Okay, so if you see, correct answer is option A. Very easy question. Now KCET basically is a mixture of easy and difficult question. Now if you want to practice the exact KCET level questions, definitely you have to consider our ABHYAS KCET 2025 test series, where you are going to get a mix of difficult as well as easy questions, so that you are prepared for your KCET. Exact time management is very essential. So in ABHYAS test series, you are going to get 35 tests, also chapter wise KCET PYQs as a form of quiz is absolutely free of cost with ABHYAS test series. So you will get 10 years KCET PYQ quiz absolutely free of cost, and you are also going to get exact real-time KCET exam pattern and timing. Time management is essential. So when you are attempting ABHYAS test series, we will be giving you a timer. Within that timer, you have to finish the paper. That is very, very essential. Many of the people, those who attempt mock test given by some others, they do not follow the timers. They give you either too much time, or they just give you a PDF. Download it, solve it yourself, understand it. So for that, you can buy a book. Why you take a test series? Right now also in this test series, you are going to get physics, chemistry, maths as well as biology. All 4 subjects will be given, and the price is 1499. So if you are interested in scoring a good rank, that is rank below 1000, then definitely you should consider ABHYAS test series. More than 1000 students are already using ABHYAS test series. So are you one of them? If not, then definitely you should consider this. Now let's continue with electric potential. So far we are discussing about potential energy. Now we are moving into potential. So are they same quantity or not? Let's see. So electrostatic potential is basically given by potential energy per unit test charge. So potential energy was when we have a charge q and we have a charge small q. Okay, so this was our test charge. This was our test charge. Okay, so if we please forgive my spelling, let me write test charge. Now this was, if you can somehow make this charge 1, then whatever energy that you get, that will be potential. Okay, so potential is only when you are moving a particular charge which is 1. Okay, now potential is given by, change in potential is given by change in potential energy divided by q. So the work done that we have calculated, the potential energy that we have calculated was for charge q. So potential will be that potential energy divided by q. That's it. Okay, so V, delta V is the change in potential, which is given by VB minus VA. Now if you take the object to infinity, if you can take one point to infinity, your starting point, basically if the starting point is at infinity, then the potential at a particular point is basically work done to bring a test charge, unit positive test charge, from infinity to that point. Okay, so work done by an external force in bringing a unit positive test charge from infinity to a point is the electrostatic potential at that point. Okay, now what else? Note, potential and potential energy are not same. Okay, so potential, as I mentioned, potential energy is basically total work done, whereas potential is particularly for one unit positive test charge. Okay, work done to bring a unit positive test charge from a point A to point B is the potential difference between the points. Potential difference is the most common in our current electricity chapter. We will see that if the work done by the external force is positive, then the potential difference is also positive. If the work done by the external force is negative, then the potential difference is also negative. Now potential due to a point charge, the derivation is important. So very easy derivation. So first of all, you have to start at infinity, reach at some point, in intermediate point, say A, and then move by a distance B. The distance is very small, dx, the external force that you have to apply to move the charge from A to B is given by F external, and that should be equals to minus of the internal force, electrostatic force. Okay, and from there you have to do the integration. So work done is given by the external force into dx, and then integrate from infinity to distance r. Okay, the distance of this point P is r, and if you do it, you will get this equation. This is the potential work done. Obviously, due to unit positive charge, if you move one unit positive charge, then the work done itself becomes potential, right? And if you do the derivation, you will get this easy derivation. You should practice it. I have covered the derivation in our Brahmastra series, so if you are interested, you can go and check that out. There I have explained in detail about this derivation. Okay, now so if you plot the graph of V versus X, the how potential changes with distance, you will get this graph. Okay, if you see here also we have E versus X graph. Okay, so how electric field changes with distance. Electric field generally starts at higher value, but it goes to 0 much quicker. So after this point, E falls faster than V. Okay, up to this point E is more, at this particular point E and V are same, and after this point V is more than E. So E, because it is proportional to 1 by r square, at smaller value of r, okay, E is much more. Okay, and at some point, but also remember E is a vector quantity, V is a scalar quantity, so there is a difference between that part as well. Anyway, now potential due to an electric dipole. So electric dipole we have studied in our electric field chapter. There we have studied what is the electric field on the axis, what is the electric field on the equatorial plane. Now potential being a scalar quantity, we do not need to calculate particularly for equatorial plane or axial position. In fact, in equatorial plane, potential energy is 0. So normally at any general position, okay, at an angle theta with the dipole moment, the potential is given by 1 by 4 pi epsilon naught P cos theta upon r square. So electric field in case of a dipole, if you remember, was proportional to, electric field was proportional to 1 upon r cube. Okay, and potential is proportional to 1 by r square. This is exclusively for a dipole. Normally for a single charge there is one value of r less. Okay, normally for a single charge it is 1 upon r square and V is 1 upon r, but for a dipole r value is increased by 1. Also, if the theta is 90 degrees, that is equatorial plane, for equatorial plane the angle is 90 degrees. So equatorial plane, along the equatorial plane electric potential is 0, because at this angle theta is 90 degrees. So along the equatorial plane potential is 0. Based on this we sometimes see some objective MCQ questions. Let's move on. An equipotential surface is a surface. So now we are moving on to equipotential surface. An equipotential surface is a surface with a constant value of potential at all points on the surface. So if we can construct a surface where electric potential is constant at each and every point, that means if I say 10 volt is the potential, the 10 volt is constant throughout the surface, then that kind of surface is called equipotential surface. The unit of potential is volt, unit of energy is joules. Okay, so joules and potential is related. So if you want what is the relationship between energy and potential, so potential is volt, okay, and that is equals to joules per coulomb. Okay, volt is 1 joules per coulomb. So the unit relationship is also established. Now, so anyway, now if you consider a point charge, okay, the electric potential is due to 1 k q by r. So if you construct circles or spheres, basically each point on this sphere, they are equidistant from the center, right? So each point will have same potential. Okay, each point will have same potential. So this point, this point, this point, they are all having same potential. So this is an equipotential surface. Similarly, if you consider any other circle, for example this circle, here also these points all have same potential. So this is also a equipotential surface. Now equipotential surface means potential on this surface is same, but it is not same as this. So two different equipotential surfaces will have two different potentials, but within a single equipotential surface, each and every point will have same potential. For any charge configuration, equipotential surface through a point is a normal to the electric field at that point. So if you want to find the electric field, suppose you want to find the electric field through this surface, it will always be normal, so this angle will also be 90 degree. So electric field is always normal to the electric equipotential surface. Okay, electric field is always normal to the equipotential surface. So here is one more example. Here electric field is parallel, so equipotential surface are also parallel planes. This is a plane number 1, plane number 2, plane number 3. So equipotential surface are also planes. Next, electric field and potential. Now electric field, as because we are discussing about equipotentials, so electric field and potential are related through this equation, Ex equals to minus dV by dx. So the derivation is also super simple, this derivation. So here we have to take two equipotentials. Now remember that when you are doing this derivation, the top electric field is pointing from the bottom surface to top surface. So this is electric field E. So if this surface is at potential V, this surface will be V minus dV. Okay, the distance between these two surfaces is dx. Okay, then this derivation can easily be done. You just need to take a point charge, move it from A to B and calculate the work done. Okay, A to B. Okay, force is given by Q into E and the work done is force into displacement, and that is equals to potential change in potential, which is minus dV. Okay, change in potential minus dV. Why minus? I will tell you in a while. So from there you can say force is Q into E into one more thing, you have to take this charge as 1 because potential is for only unit positive test charge. Okay, so Q is not there, so E into dx equals to minus dV. So E will be equals to minus dV by dx. Easy derivation, practice 2-3 times. I have done in detail in our Brahmastra series. Now electric field is in the direction in which the potential decreases the most. So that's why there is a negative sign. So the electric field points from high potential to low potential. Not only that, in the particular direction where the decrease is highest. Okay, so if you see that in their electric field is also decreasing in this direction, electric field is decreasing also in this direction. But if you consider from A to B, if you reach from here to here, the rate of change is much smaller compared to this change. Okay, so electric field only points from higher potential to lower potential, and also in the particular direction where the decrease is steepest. Steepest means the rate of change is highest. Okay, second, electric field is normal to the equipotential surface at every point. I already mentioned it. Next, potential energy at in an external field. Now, so basically what we have done, so we started with potential energy, then we traveled into potential. Now again we are going back to potential energy, but we have removed all the charges. We are only now focusing on external field. External field means some electric field is already there established due to some current carrying conductor, due to some capacitor. There are multiple ways to establish an electric field. So some electric field is there and you are placing a charge in that. So what will be the potential energy of that? So single charge, when a charge small q is placed in an external electric field, the potential energy of the charge is given by small q into V. Here V is the electric potential at that point. So basically same as electric field and force. So we started with Coulomb force, moved on to electric field, then we came back to force, right? If you remember our previous chapter. Similarly, here also we started with potential energy, then we moved into electric potential, then again we are coming back to potential energy in terms of potential, right? So here the potential energy of any point is given by charge into electric potential at that point. Okay, two charges are there. Now it is for one charge. Now if there are two charges, okay, how can we calculate the potential energy of this system? Okay, so there is a possibility that only two charge is there. There is a possibility that two charge and external field is also there. Okay, so two charge and an external field is there, then the electric field will be given by Q1 into Vp. So not AB, PQ. Okay, suppose this is P, this is Q, this is Q1, this is Q2. Okay, so in that case the potential will be Q1 into Vp, that is the potential of this point, and Q2 into Vq plus 1 by 4 pi epsilon naught Q1 Q2 by R. Now if there are no external field, if the electric field is 0, then Vp equals to Vq equals to 0. So in that case potential energy will be simply 1 by 4 pi epsilon naught Q1 Q2 by R. So this formula also you have to remember. In KCET and board exam, if some question comes based on this concept, mostly there will be no external field. So if there are no external field, then you just need to use electric potential energy is Q1 Q2 by R, K Q1 Q2 by R. Do not confuse with Coulomb's law. In Coulomb's law there is R square. In potential energy there is only one single R. Okay, many students confuse. Anyway, system of charges, now we are discussing of about three charges. Now we only have three charges, external field is 0. So we have Q1, Q2, Q3. The distances are given R12, R13 and R23. Now this is a very particular situation. So how can we find the potential energy? Suppose we have one charge. First charge when you are bringing, there is no work we require, no work done is required because no electric field is 0, potential is 0. So if you have only one charge, then you can move it anywhere without doing any work, right? So first charge when you are bringing it here at this point, okay, work done is 0. Now you are bringing the second charge. Now when you are bringing the second charge, there is an electric field present due to the first charge. So you are doing some work against the electric field of the first charge. So to bring the second charge, you are doing some work. That work is being stored in the form of potential energy. Secondly, when you are bringing the third charge, now you are doing the electric field due to first charge as well as the second charge. So the total energy of this system is not a simple one, but it is like this. U equals to 1 by 4 pi epsilon naught Q1 Q2 by R12. So what you have to do, you have to multiply the charges and divide them by their distance. Similarly, Q1 Q3 divided by R13 plus Q2 Q3 divided by R23. Now here a very important point to remember is that the final expression for U is independent of the way the configuration is assembled. The potential energy is given by present state of configuration and not the way the state is achieved. So this formula is independent of whether you brought Q1 first, next Q2, last Q3, or you have achieved it by bringing Q2 first, then Q1, then Q3. So the order of which the assembly is being assembled, it is independent of that order. You can bring any charge first, any charge next. Only thing that has to be careful about the distances. So distances has to be same. If distances are same, then the way you have assembled it, the potential energy is independent of that. Next, potential energy of a dipole in an external field. So we have done a derivation where we have calculated the torque acting on a dipole in an external electric field. So dipole, so first we have done the potential energy due to a dipole. Now we have taken the dipole and bring it in external electric field. Okay, so external electric field, same as last chapter. right? So when you bring the dipole in an external electric field, what happens? The dipole also gains some potential energy. So normally that work, in case of work, generally we do use force, but in case of dipole we will use torque. Okay, torque is P cross E. Okay, so it is basically torque is equal to PE sin theta. Okay, and it is a rotational motion. So how to calculate work done? So remember, potential, whenever we are talking about potential, it is basically work done. Okay, potential energy, whenever we are talking about that, then it is basically work done. If it is a charge which is +1, then it will be potential. If it is not +1, then it will be potential energy. For a dipole, we do not know whether it is +1 or not, so it will be potential energy and not potential. So work done will be given by torque d theta. Just put it and integrate it from angle. Starting angle will be 90 degrees and final angle should be some angle theta. Okay, because at pi by 2 it becomes 0. So now you have to integrate it, and if you do the integration, you will get the potential energy is given by minus PE cos theta. Okay, the potential energy will be given by minus PE cos theta. This can be directly calculated from this. Okay. So this is also potential energy, so you will write it as U, right? And this can be written as dot product. Cos theta means it's a dot product, right? Very simple. Derivation is also very simple, easy. Only thing you need to remember, the limit of the integration should be pi by 2 to theta. So basically the dipole was at this position, then you are rotating it at some angle. Okay, the starting angle is not this but this. That is the major difference. Anyway, electrostatics of conductor. This is some few points mentioned in this chapter where some information is given about conductors. So first of all, metallic conductors contains mobile charge carriers, namely electrons. Mobile charge carriers is nothing like your mobile phone. It's a charge carrier. That means it's basically something which carry charges, free charges. Okay, free charges are called mobile electrons. In a metal, the outer or valence electrons part away from their atoms and are free to move. Okay, in semiconductor chapter we will study a little bit more about it. So valence electrons do not come out of the metal, but they move from valence shell to conduction shell and forms conduction band. And in conduction band, the electrons present, they are free to move. These electrons are free within the metal but not free to leave the metal. Very important. So these electrons are not, they cannot come out of the metal of their own will, but they are free within the metal. So within the metal they can do whatever they want, but they cannot come out of the metal. Free electrons form a kind of gas. They collide with each other and with the ions and move randomly in different direction. Okay, so they collide with each other, they move in the random direction, and because of that we basically get electrical resistance. In an external electric field, they drift against the direction of electric field. So if you apply an external electric field, then the electron will slowly start moving in the opposite direction, and that motion is called drift motion. Okay, now let's move on. Points to remember: inside a conductor, electrostatic field is 0. So electric field is 0 inside a conductor. Okay, so if you consider an electric conductor, okay, what happens is that when you apply an electric field, external electric field to a conductor, the conductor develops an electric field which is exactly opposite to that of the external electric field. So basically inside the conductor, the internal electric field and the external electric field, they cancel each other, and that's why net electric field is 0. If you give a charge to it, the charges will stay on the surface, and because of that inside the electric field will still be 0. If you keep it in an external electric field or you charge it using charge, in both cases the net electric field inside a conductor will always be 0. Okay, at the surface of the charged conductor, electrostatic field must be normal to the surface at every point. So if you consider a conducting surface, the electric field is normal at each and every point on the surface. Okay, the angle is always 90 degrees no matter what. Okay. The interior of a conductor can have no excess charge. It is slightly tricky, the language is slightly tricky because obviously otherwise you might mean something else. Okay, in static situation, any excess charge must reside at the surface. This line is much easier to understand. So if you add some charge, okay, if you add some excess charge means some extra electron you add or you remove some extra electron, the way you want to charge this object. So if you charge this object by adding or removing some electrons, the charges will not stay inside, the charges will always stay on the surface. Okay, like ping pong balls floating on a water. Okay, charges will always stay on the surface, the charges cannot go inside. Okay, they are not allowed inside. Excess charges are not allowed. Okay, inside is the inside part of a metal is charge free. Inside part is not charge free, but if there is a positive charge, there is equal number of negative charge as well. So inside the conductor, basically atoms, they have equal number of electrons and protons. So that's why inside the conductor no excess charge. Excess charge means extra charge. Okay, inside there will be charges, but the charge are all equal. Positive and negative are equal and they will cancel each other. So that's why if you add any extra charge, they will float on the surface. Electrostatic potential is constant throughout the volume of the conductor and has the same value on its surface. Electric field at the surface of a charged conductor is given by E is equal to sigma by epsilon naught n cap. Okay, based on this there was a KCET question a few years back. Now, electrostatic shielding, a very important property of conductor. Electric field inside a cavity in a conductor is 0. What else? Now we are moving on to dielectrics. Dielectrics are basically insulating materials. Dielectrics is nothing fancy, the name is fancy, but it is basically insulating materials. Okay, dielectrics are non-conducting substances. In contrast to conductors, they have no charge carriers. Basically they are it's a fancy name for insulators. Okay, fancy name for insulators. Dielectrics are insulating materials. Okay, now insulating materials, even though we say they do not conduct electricity, they do have some purpose, right? Otherwise, why do we need to study about insulators? We can say okay, there are some objects which do not conduct electricity, delete that. Okay, but insulators do also help us in some way, especially in static electricity. Let's see. It turns out that external field induces a dipole moment by stretching or reorienting molecules of the dielectric. So even though dielectrics do not have any free electrons or free charge carriers to carry the current, but if you apply an external electric field around the dielectric, okay, that dielectric tend to produce an internal electric field because of the reorientation of the positive and negative charges, because all molecules, atoms, they all are basically formed by electron and protons. So every atom has electron and proton. In metals, electron and proton, they reorient themselves such a way that the electric field cancels. In case of dielectric, the electric field does not cancel, but it has a property of reducing the electric field. Okay, so the collective effect of all the molecular dipole moments is the net charges on the surface of the dielectric, which produce a field opposite the external field. So the opposing field so induced does not exactly cancel the external field, it only reduces it. Extent of the effect depends on the nature of the dielectric. So basically metal cancels the electric field altogether, but dielectric does not cancel the electric field but reduces it. And for us, cancelling altogether is not very important, but reducing it also very important. Cancelling can be helpful in some cases. Electrostatic shielding, for example, is useful to store some high value equipments, highly sensitive electrical equipments, but dielectrics are also essential because it does not cancel it. We may need to reduce the electric field without cancelling it. So in that case, dielectric is very, very handy. So if you see the diagram, here we have electric field applied, external electric field E naught, okay, and inside the dielectric there is, so this is a conductor. Inside the conductor, external electric field and internal electric field, they were equal. But in case of dielectric, what happens? They still orient their positive and negative charges similar way, but the orientation does not happen in equal amount like in conductor, because electrons are not free. So all the electrons are not allowed to go to the other side. All the protons are also not allowed to go in the direction of electric field. Some of them organize, some of them still remain disorganized. So based on this, they develop an internal electric field. So internal electric field, as you can see in this diagram, is not same as the external electric field. So they are not able to cancel each other, but net electric field is not zero. Net electric field is not zero. The opposing field is so introduced, it does not exactly cancel the external field, it is only reduces it. The extent of the effect depends on the nature of the dielectric. Now, because we are talking about nature of the dielectric, so dielectrics basically divided into two parts. We will come to that. Dielectric constant or relative permittivity. So before going into that, we have to learn some brief concept about dielectric constant, sometimes also called relative permittivity. Okay, it is basically permittivity of the medium divided by permittivity of free space. So if you remember, in Coulomb's law we discussed that if the charges are placed in vacuum or free space, the formula is valid. But if they are placed inside a dielectric medium, and I told you that I will discuss about dielectric medium in my next chapter. So dielectric medium means, suppose water, you can take water as a dielectric medium, or resin, okay, resin which is used to polish the wooden surface, so that liquid can be considered as dielectric medium. So if you take two charges, if you put the charges inside that dielectric medium, the force will reduce, okay, and that is because of this dielectric constant. So dielectric constant is given by permittivity of the medium divided by permittivity of free space. Okay, dielectric constant of metals is infinity. So based on this, we see one objective question came in one of your district papers few years back. So that's why I have included it. Dielectric constant of metals is infinity, not zero but infinity. Now let's see one MCQ question. Two charged spheres separated at a distance small d exert a force small f, capital F on each other. If they are immersed in a liquid of dielectric constant K, then what is the force? So we know that normally force is proportional to 1 by r square, that is Coulomb's law. Now if you put this medium inside a dielectric medium, then the force, new force, is proportional to r root k whole square. Okay, so it will be F dash equals to 1 by r square into k. Okay, so if you divide this, we get F dash by F equals to 1 upon r square by k divided by 1 by r square, so it will be 1 by k. So F dash equals to F by k. Now if you are thinking, sir, how you write this equation, this one, okay, Coulomb's law is fine. So for that you have to watch my previous lecture, electric field and electric charges and field. There I have explained why this formula is coming and how for dielectric medium you can simply replace r by r root k. Okay, so this is the equivalent distance in case of a dielectric medium. Okay, so if you know this, you can directly write it. If you don't know it, you have to start from Coulomb's law, then replace it. That will be a longer process. Okay, now let's move on. Now as I mentioned, dielectrics can be divided based on their properties. How much it will oppose the external electric field, that depends on the property of the dielectric. So dielectric can be classified into two types of dielectrics: non-polar dielectric and polar dielectric. Okay, so the polar and non-polar dielectric, difference between them, what is a polar, what is a non-polar, is very common in your PU exam. So you have to memorize the type and some diagram as well. Also try to understand the concept behind why it is non-polar, why it is called polar. Polar means, obviously the term is very clear, polarity, positive and negative. Non-polar means positive and negative are there. Obviously all atoms will have positive and negative, but they are locating at the same place. Okay, their centers coincide. So in a non-polar molecule, the centers of positive and negative charges coincide. Now you might say that, sir, we have a proton, we have an electron which is orbiting around the proton, or suppose two electrons. Okay, electrons are orbiting around the proton. How can their centers be coincide? Okay, because if you see that proton is over here, okay, electron is some distance over here, in this side, also in this side. How can their center be coincide? Centers coinciding means if you take the average of the position of the electron, okay, average of the position of the electron, then basically if it is a circular path, then its center is always at the center of the circle. Okay, even it's a single electron, if it is a double electron, triple electron, okay, unless and until it's there are some hybridization, okay, for normal cases, mostly electrons will have orbiting around the nucleus, they will have its center at the center of the circle where the protons are located, where the positive charges are located. So in that case, centers of positive and negative will be coinciding. There are some cases for due to hybridization, due to bond formation, that position can change, and that's why we see polar and non-polar dielectrics. Okay, the molecule then has no permanent or intrinsic dipole moment. Molecular level, at molecular level, the dipole moment of non-polar dielectric is 0. Example of non-polar molecules are oxygen, hydrogen, carbon dioxide. Okay, molecules which are because of their symmetry, they have no dipole moment. Even carbon dioxide is also non-polar dielectrics. Next, and if you see that electric field diagram, so normally in the absence of electric field, positive and negative all are located at same place. If you apply an external electric field, positive, negative do separate because of the effect of the electric field, and electric field is they reduce the external electric field by some extent. Now polar molecules or polar dielectrics, a polar molecule is one which the centers of positive and negative charges are separated even when no external field is applied. Now how it is possible? For example, water. Okay, water, if you consider water, okay, the angle is about 120 degrees. Okay, what happens? The electron pair which is being shared by hydrogen and oxygen, okay, the electron pair shifts towards the oxygen. Okay, and because of that oxygen becomes negatively charged and hydrogen becomes positively charged slightly. Okay, so that is -2 delta, and this is plus delta, and this is also plus delta. Right, so that's why we see a net dipole moment. So net dipole moment, we see what is the meaning of net dipole moment? The meaning is that basically they have a dipole moment and they are polar molecules. Okay, so water is an example of polar molecules. So you may have learned in your chemistry that water is an universal solvent. Please explain why. Because water is a polar molecule, it can bond with some of the inorganic salts, also it can make bonds with the organic salts as well. That's why it's an universal solvent. Right, now so such molecules have a permanent dipole moment. Example, HCl, H2O, carbon monoxide is also polar. Note, in a polar crystal the net dipole moment is 0. This is because the molecular dipoles are randomly arranged. So at molecular level they have some dipole moment. But if you consider the crystal level, at crystal level the net dipole moment is still 0. So if you take one molecule, you will find some dipole moment. But if you take the entire object together, the net dipole moment will still be 0. So remember, this is very interesting. And when you apply an external electric field, what happens? That some of the dipoles gets arranged according to the external electric field, and that again it also reduces the external electric field. Okay, now Polarization, very important concept. Whether a polar or non-polar, a dielectric develops a net dipole moment in the presence of an external electric field. The dipole moment per unit volume is called polarization and is denoted by P. This is electrical polarization, by the way. Okay, this is not optical polarization, this is called electrical polarization. For a linear isotropic dielectric, isotropic means if you move along the dielectric, the density remains same. Okay, mostly they are isotropic. So linear isotropic dielectric, the polarization is defined by epsilon naught chi e. Chi e, this is chi. Okay, spelling is chi, chi e into E. Okay, where chi e is a constant of characteristic of the dielectric and is known as electric susceptibility. This is called electric susceptibility of the dielectric medium. It's a dimensionless quantity. It's a dimensionless quantity. Electric susceptibility is a dimensionless quantity. And this is dipole moment per unit volume. Net dipole moment per unit volume. Very important. It's net dipole moment per unit volume. So there might be one case they might ask you what is the dimension of this quantity. So dimension of this quantity is basically P is net dipole moment divided by unit volume. So what is the dimension of, so dimension of capital P is actually equals to dimension of small p divided by volume. So dimension of small p is LAT, and dimension of volume is L cube. So the net dimension is L to the power of minus 2 A into T. So this question is also very popular in terms of MCQ question. Okay, so if you remember the dimension of dipole moment, you can find the dimension of polarization as well. Now let's move on. Capacitor and capacitance. So this is now we are in the last leg of our discussion. Capacitor is a device that is used to store charges. A capacitor is a system of two conductors separated by an insulator. Usually in practice, two conductors have charges capital Q and minus Q with potential difference V equals to V1 minus V2. Q is called charge of the capacitor, though in this fact is the charge of the one of the conductors, the total charge of the capacitor is 0. So basically capacitor does not necessarily mean parallel plate capacitor, but it can be any conductor. But for 99.99% of our life and in future, unless you are very specific into designing certain kind of capacitors, you will learn about parallel plate capacitor only. Okay, and the symbol is also parallel plate capacitor. Okay, so 99% of percent of your entire life, if you study engineering, no matter what, unless you are synthesizing with a very specific kind of request, very specific kind of circuit, you may need to design a particular type of capacitor. Otherwise we will always discuss capacitor means parallel plate capacitor. Okay, so don't mind me if I say capacitor is parallel plate capacitor. Because of that fact only, capacitor symbol is also like parallel plate capacitor. Suppose this is plus Q, this is minus Q. So when you say the charge of a capacitor, we only say this is the plus Q, normal Q. But if you consider the total charge of the capacitor, total charge of the capacitor is 0, plus Q minus Q. So total charge means you take the capacitor, you short it, so charge will destroyed immediately. So that is the total charge. But we that will be a waste of energy. Capacitor is used in a circuit where charges are stored, potential has to be maintained at some value. Then in that case capacitors are used. So that's why even though the potential total charge stored is 0, it is still very, very useful. And when we say the charge of a capacitor means charge of the positive plate, which is plus Q. Okay, this is an important statement that total charge is capacitor is 0, because based on this you might get a MCQ question. That's why you have to remember that the charge of the capacitor leaks away due to the reduction in the insulating power of the intervening medium. Now because of the medium which is present between the charges, okay, there is an electric field present over here. Electric field is present from positive to negative, and electrons from the negative plate slowly starts to come in this direction, and they try to destroy the capacitor charge stored in the capacitor. So if you store a charge in a capacitor for a long time, it will go away. Or if you try to store a very high amount of charge, because of the high electric field, suddenly all the electrons will come from negative to positive, and again the capacitor will discharge. Okay, and in some cases capacitor may get destroyed as well. Okay, now the potential difference V is proportional to Q, and the ratio Q by V is constant. So suppose we have a capacitor plate, the potential difference between the plates is V and the charge stored is Q. So Q by V is a constant, and that constant is called capacitance of the capacitor. That constant is called capacitance of the capacitor. The constant C is called the capacitance of the capacitor. C is independent of Q or V. So you might feel that what is C is equal to Q by V. How can you say C is independent of Q by V? Okay, C equals to Q by V, perfect, but the ratio of Q by V is constant. So if you increase Q, V will increase proportionally. If you decrease Q, V will decrease proportionally. Okay, so C will remain constant. Okay, unless Q is 0. Okay, this formula is not valid when Q is 0. Otherwise, for any other case, C equals to Q by V, and C is independent of Q by V because Q and V are related to each other. They are locked, phase locked. For example, Earth and Moon are phase locked. No matter where the Earth is going, same side of Moon is following us. We do not see the back side of the Moon, which is called dark side of the Moon. Okay, now the SI unit of capacitance is Farad. Farad is 1 coulomb per volt. In practice, Farad is a very big unit. The most common units used in practice are microfarad, nanofarad, picofarad, etc. Okay, from the above equation we can see that large the value of C, V is small for a given Q. So if you can increase the value of C, okay, there are ways to increase the C value. Okay, you can store a high amount of charge, but the voltage, that is the electric field, will remain low. So if I want to design a capacitor where I want to store a high amount of charge at low V, I have to think such a way that I can have a very high capacitance. High capacitors can store a large amount of charge, but the potential difference will still be small. Okay. The parallel plate capacitor. A parallel plate capacitor consists of two large plate parallel conducting plates separated by a small distance. So that's what I was talking about. So if you say two parallel plates separated by a very small distance, this is a parallel plate capacitor. And most of our practical purposes, 99.9% of our capacitors are basically parallel plate capacitor, except some specific uses. Okay, now the space between the plates can be filled with dielectrics to increase its capacitance. Now if you fill the space with the dielectric means polar and non-polar. So if you mica sheet, for example, is a very good medium that is used inside a capacitor. Okay, mica sheets are very thin layer of insulating medium. Okay, so they are used inside capacitors to insulate the plates. Okay, now capacitance of air capacitor. Air capacitor means inside the plates only air is there. This is an hypothetical capacitor, not a single practical capacitor uses air. Okay, we did when I was a student during my MSc days, we did a experiment to find the dielectric constant of ice. So there we have used normal air for a capacitor. The experiment was little tricky and difficult because the capacitance was very, very low. Anyway, so except some specific cases, air capacitors are not used. But for your class, for your PUC 2, second PUC, the air capacitor is most common. For KCET level, slightly higher. The next we are coming next. So capacitance for a air capacitor is given by A epsilon naught by D. So what is A? A is area. Okay, D is the distance between the plates. okay, and epsilon naught is free space permittivity, you already know. So this is the formula for air capacitor. The capacitance depends only on the geometry of the system, I already know. Next, move on to effect of dielectric on capacitance. So if you insert a dielectric medium between the capacitor plates, okay, what will happen is that it will reduce the electric field. So because of the reduction of electric field, the capacitance will increase, okay, and in that case the capacitance will become A into K epsilon naught divided by D. Okay, so A into K epsilon naught divided by D. So capacitance increases by K times. So capacitance increases by K times. So if you insert a dielectric medium of dielectric constant K, K is dielectric constant. Okay, then it is K into C. Thus the capacitance increases. So this is a way to increase the capacitance, and based on if you are appearing for KCET exam, then this dielectric constant is very important in the formulas, in the numerical problems, but in board exam you can skip the dielectric portion, dielectric constant part. Now combination of capacitors similar to that of combination of resistors, combination of capacitors is there. Series combination of capacitor means they are connected one after another, and in series combination the charge that is flowing is constant. Okay, the charge that is flowing in the capacitor is constant, so each of the capacitor will be storing the same amount of charge. Okay, and the equivalent capacitance is given by 1 by C1 plus 1 by C2 plus 1 by C3, etc. Now for two capacitors, C equivalent is C1 C2 by C1 plus C2. Okay, and for parallel combination, C equivalent is very simple. C equivalent is equal to C1 plus C2 plus C3 plus ... Okay, clear? Now last topic of the day, energy stored in a capacitor. So when we are talking about capacitor basically is a device which is storing energy. That is the main purpose of the capacitor. Now how much energy it will store? The energy, obviously the derivation is not part of the syllabus. Energy stored in a capacitor is given by half CV square. Okay, half CV square is the energy stored, and half Q into V is the alternating form, and half Q square by C is again the energy stored formula. So these are the same formulas, only three different forms. Now energy density is basically energy stored divided by volume. Okay, energy density is represented by small u, which is basically total energy stored divided by volume, and that can be expressed in this form. This form is important for PU, okay, because you might see a question, express the energy density of a capacitor and explain the terms. So small u equals to half epsilon naught E square. Small u is the energy density, epsilon naught is free space permittivity, and E is the electric field between the plates. E is the electric field between the plates. So electric potential energy stored in a capacitor is basically in the form of electric field. Okay, stronger the electric field, more energy it can store. Okay, so this is the main theory portion of this chapter. Solve one more last question. A 10 millifarad capacitor has been charged to a potential of 100 volt. Suddenly it explodes. The energy given out is, so if a capacitor explodes, how much energy it will give out? The capacitor will give out the energy that it had stored, right? So how much energy can a capacitor store? The energy stored by a capacitor is half CV square. Okay, so if you know that, you can solve this question. C is C here is 110 millifarad. I am not sure it is milli or micro. Let's start with millifarad only. Milli means 10 to the power of minus 3. Okay, so C is 10 to the power of minus 3. V is 100 volt. Let's see if I get an answer or not. So half C is 10 into 10 to the power of minus 3, and V square means 100 square. Okay, so half into 10 to the power of minus 2. Half into 10 to the power of minus 2, 10 into 10 to the power of minus 3 minus 2 into 100 square. 100 square means 10 to the power of 4. Okay, 100 means 10 square. Okay, so 10 square whole square equals to 10 to the power of 4. So we get half into 10 to the power of minus 2 into 10 to the power of 4. That will be, sorry, it will be 10 to the power of plus 2. Minus 2 plus 4, that is 10 to the power of plus 2. 10 to the power of plus 2 means what? 100. So 100 by 2, that is 50 joules. The energy given by it is 50 joules. Not 10 to the power of 5, not 50 millijoules, but 50 joules directly. Okay, so the capacitor will give out energy of 50 joules. This kind of questions are also common in KCET and your state board exam. In 1 year they give capacitor is charged to certain voltage. What is the energy stored? Half CV square is the formula to use. Okay, now formula sheet, again I am giving you a formula sheet along with this chapter. So download the PDF and you will get the formula sheet. Okay, so this is the formula sheet for the entire chapter in 2 pages. Okay, parallel combination, series combination, everything is covered in this formula sheet. Okay, if you liked this video, then don't forget to give it a thumbs up. Also don't forget to subscribe to our channel. Subscription are very important for us. Also remember that if you want to download the PDF of this lecture and all the future lectures, don't forget to join the WhatsApp community. Right, I'll be back with a new chapter very soon in our Masterstroke series. Till then, bye.